In this short video we'll do second derivatives. What are they? They are the derivatives of the first derivative. The first derivative of the first derivative. The sign there is like that. So d on the power 2 by the x on the power 2. What do they represent? They represent concavity of the original curve. So if the second derivative is greater than 0, we have the function original concave up. If the second derivative is less than 0, we have the function that is concave down. So let's do a table to summarize our first and second derivatives. Okay, so we're here and here. Here. So table will have three rows and 3 columns. In the first column we will have the second derivative that is greater than 0. Then we have the second derivative less than 0, and we will have the second derivative equals to 0. That's our first column. 3 columns. And our first row will be the first derivative greater than 0. Then we'll have the first derivative less than 0. And we will have the first derivative equals to 0. So, when the first derivative is greater than 0, we know that tangent line points up. We have 2 cases here because of the concavity changes. We don't know whether it changes from concave up to concave down, because now first derivative is less than 0 and the first derivative is equals 0. So now let's draw the function line, the original. So concave up, first derivative is greater than 0. Concave down, and now the first derivative equals 0. These points are called points of inflection because that the concavity changes from one to the other. So it's point of inflection. Points of inflection. Points of inflection. Change in concavity. Here the function is concave up. The function is concave down. And the change in concavity. And here we have again concave up, concave down, and the change in concavity. Sorry, it's the other way around. Change in concavity. So this should have been down to the line. So what happens here is that these points where the first derivative is equal to 0, we call them stationary points. And so this is local minimum, local maximum, and here they will be called the stationary points of inflection, because these are stationary points here. Stationary points in this direction. So stationary points of inflection. So what happens, there are cases where the first derivative is 0 and the second derivative is 0 at some point of the independent variable x. But at that point is not a point of inflection, which means the concavity doesn't change. So in that case, only for the case where we have first derivative is equal 0 and second derivative is equal to 0, in the case that we want to make sure that we have points of inflection, we will check the sign of the second derivative around these points where the second derivative is. So at point when x equals 1, we have that second derivative is equals to 0, and x equals 2, we have second derivative is equals to 0. But to make sure that there are points of inflection, we check the sign. So we test the function for the value, say 0, and the value for 1.5, and see, for example, we have discovered that before 1 the second derivative is greater than 0, and after 1 the second derivative is negative, and then here the second derivative is also positive. Therefore this point, because the derivative around, sorry, not that, around point 1, so number 1 is a stationary point of inflection because the sign changes. But and the second in this one is also. But if we had a case where, say for example, here we had a minus sign for the second, so for the second derivative be negative, then there will be a case then minus minus, so therefore this one wouldn't be point of inflection, not a point of inflection in that case. So that's all for the second derivatives.